Hey everybody, I'm Jordan Kern. I'm an assistant professor in the Department of Forestry and Environmental Resources at NC State. And if you are watching this, it means I couldn't be in class in person today. And so I'm going to be trying to lead this case study 5B on planning for a low carbon and resilient power grid virtually. So just to start out, a little bit about me. My background is sort of a cross between environmental science and environmental engineering. I got all my degrees from UNC Chapel Hill. From 2015 to 2018, I taught at UNC and did some research. A lot of my research focuses on understanding the vulnerability of electric power systems, both from a financial and economic perspective, but also a physical reliability perspective, to extreme events, including drought and heat waves. And then in 2018, I joined the NC State faculty in FER. And a lot of what my group does in terms of research at NC State is building open source computer software that allows us to then sort of stress test the power grid for vulnerability to extreme events. So I do like questions, although because this is virtual, obviously there's not going to be much of an opportunity to field those. Um, just on a personal note, I'm married. I have two kids, twins actually, a boy and a girl. And my wife is a physician scientist at Duke. Here, a picture of my kids. These are old pictures. They're almost 10 now. I think they were probably 4 or 5 in these pictures. So today we're going to talk about a big question. The big picture question for today is how should electric utilities and the general public and publicly elected bodies that are in charge of regulating electric utilities balance the costs and benefits of, one, reducing greenhouse gas emissions, which is the main thing we have to do to reduce the probability of really bad, climate change in the future, and two, how do we protect infrastructure? And electric power systems or the grid would be a key piece of infrastructure from the negative impacts of climate change, like increased frequency and severity of extreme weather. So learning objectives for this case study are, there's a couple, right? So first, we want to be able to describe the different major parts of the electricity grid and how each contributes to climate change and how each is vulnerable to extreme weather. You should be able to analyze information about the carbon dioxide footprint of the North Carolina grid, and its reliance on different generating technologies. And then be able to synthesize information to develop a plan for improving the sustainability and resilience of the North Carolina grid moving forward. So a lot of this is going to be contained in the readings and some of the videos that you were supposed to watch before this case study. But I do want to give sort of my version of the 101, what is the grid overview. So when we talk about electric power systems that we all interact with, a lot of times people refer to that as the grid or a bulk electric power system. And what that means is a connected network of generators, which are places where the electricity would be produced. There's all different types of generators that get used to do that. Most of them rely on spinning some kind of coiled conductor within a magnetic field to induce electrical current. And they're all kind of different in terms of what force is causing that coiled conductor to spin, right? In the case of fossil fuel power plants like coal and natural gas, we're combusting those. And then the heat from that combustion process creates steam. And then the force of that steam expanding spins a turbine to generate electricity. In the case of something like wind power, we're using wind speed to spin something to generate electricity. Hydropower, we're using the force of falling water to spin something to produce electricity. In the case of nuclear, we're using heat from a fission reaction to create steam to spin something. And the only exception is really solar, right? So we're using electrochemical processes to convert sunlight into electricity from solar panels. So there's all sorts of different ways to generate electricity, and once we produce that electricity, it typically would go through a transformer at a substation to increase the voltage of electricity to very high levels, and then that electricity is sent out over high voltage transmission lines over very long distances to the approximate location where it's going to be consumed. And then it goes through another substation where the voltage is decreased, and then that electricity is sent out over lower voltage lines to homes and businesses. So if you think about the sort of, the United States as, as a whole, we can think about the grid being organized a couple of different ways. Electrically, things are mostly connected. If you go out to the Western United States, all the blue area that's shown in that map on the left is, in theory, electrically connected, meaning you could send electricity from Seattle to California, or from Colorado to California. And if you go to Texas, which is shown in green here, or most of Texas is shown in green here, that's a separate system, and it's sort of electrically connected, but disconnected from the Western United States. So Texas is its own kind of island. You can't send electricity from California to Texas or from North Carolina to Texas. And then in the East, we have another big electrically connected system. So you can send electricity, in theory, from Chicago to North Carolina or from Boston to North Carolina. That doesn't happen very often. And then if you look on the right-hand side, that's sort of talking about the different types of entities that are in control of electric power systems. In North Carolina, for the most part, we have a vertically integrated utility, Duke Energy, that kind of owns and operates everything. But if you go to other places in the country, you have lots of different utilities that are operating under what are called system operators. And so you might have lots of utilities that are kind of working together to meet electricity demand. And all the areas that are colored in that big map of the United States in the top right show areas where a lot of utilities are kind of working together to meet electricity demand. So one of the themes that we're going to talk about, or came up in some of your readings, or we're going to touch on towards the end of the exercise today, is the vulnerability of the grid to extreme weather. And this can happen a lot of different ways. So the grid is vulnerable to wildfire, which can damage transmission lines. This is also kind of a tricky example because malfunctioning electrical equipment can actually start wildfires, and has famously done so in California. Extreme temperatures, both hot and cold, dramatically increase demand for electricity. They can cause freezing issues, transmission line outages, and inefficiencies at power plants that can cause them not to run properly. Hurricanes can dramatically influence the functionality of electric power systems. Usually we think about that being caused by wind speeds that knock over trees into power lines, but also flooding can impact different parts of the electrical grid as well. And that figure in the bottom left is showing a flooded substation in North Carolina from Hurricane Florence. Drought can also impact electric power systems, and one of the main ways it does that is by reducing the availability of water to produce hydropower. Now, most of the United States doesn't rely on hydropower that much, but the Western United States, especially the West Coast, California and the Pacific Northwest, rely a lot on hydropower, and when drought impacts that area like it has done this year, they lose the ability to produce electricity using hydropower, and they have to use other more expensive and more polluting types of generation. And then winter storms, severe winter weather, especially on the East Coast, can cause all sorts of different problems, and has famously caused issues in Texas in 2021, which left people sort of in a dangerous place without power for weeks on end. So the cost, all of this is the impacts of extreme weather on the grid are within this larger context of growing costs, economic costs associated with extreme weather in the United States. So this figure is showing gradually increasing numbers of billion-dollar extreme weather events, meaning weather events that cost at least $1 billion in the United States. And all the different colors represent the total costs and what type of extreme weather event was responsible. And so you see this larger sort of increasing trend. And this trend is increasing because of climate change, but also because of what's called growing value at risk, meaning we're just building a lot more infrastructure in the path of extreme weather. And so that causes the losses to increase. And so the specific damages associated with extreme weather that are caused by damaged electric power infrastructure are on the order of $25 to $75 billion a year. And so that could be damaged electrical equipment or economic losses associated with the suspension of electricity service. So the grid is really vulnerable to extreme weather. And at the same time, we need to decarbonize the grid, meaning rapidly reduce greenhouse gas emissions that come from electric power systems in order to meet the sort of climate crisis. And so this figures I took from Saul Griffith's Rewiring America, and each one of these lines shows a different emissions reduction trajectory that we could be on to satisfy essentially the sort of scientific consensus of needing to reduce emissions so that we stay within a 1.5 degrees Celsius increase in average air temperatures on Earth. And all the different lines vary in terms of when they start decreasing and then how steeply they decrease. And so the lines that start decreasing earlier are less steep. And all that is to say that the longer we wait to reduce carbon emissions, the more drastic those emissions are going to have to be if we want to avoid the really significant negative impacts associated with climate change. And increasingly, there's some consensus about one of the cheapest, potentially the fastest way to decarbonize the U.S. economy is to electrify everything. So electricity production is only one piece of where greenhouse gas emissions come from. But if we were to decarbonize the electrical grid and expand electricity service into transportation, meaning we're going to electrify vehicles, electrify different parts of industrial use of energy, commercial and residential heating and cooling, and all of that energy was coming from a grid that had then eliminated its dependence on coal and natural gas, then all of the primary energy that would be being used in these different sectors would be clean and zero carbon. One of the downsides potentially of decarbonizing, especially using wind and solar, which is happening more and more, dramatically increasing our reliance on wind and solar because we're trying to decarbonize the grid, is that variable renewable energy, so wind and solar, have a lot of issues related to them. Some of those issues are geographical, meaning we don't always have wind and solar where we want it to be. And some of those have to do with the uncertainty and intermittency of when those resources are available. So wind is not constant, solar is not constant. And it's likely that we're going to have to rely on a variety of different solutions, some of which are cheap and some of which are expensive, to help integrate more wind and solar into the grid. So that means that if you think about climate change and extreme weather growing in terms of frequency and severity, the grid is going to be more exposed to weather or severe weather or weather risk in the future. But also because we're depending more and more on wind and solar, which are inherently meteorological, system operators and utilities are now going to be much more dependent on or sort of exposed to weather risk in that area as well. And one of the complicating facts here is that each one of these sort of separate challenges could make the other more difficult to solve. So we're not going to get too much into that today, but I did want to sort of set the stage for some of the challenges that utilities like Duke Energy might face when they're thinking about how to decarbonize the grid, or what a utility commission or the General Assembly in North Carolina might face when they're thinking about the best way to decarbonize the grid, while also maintaining a high degree of reliability and low costs, so that electricity consumers don't have to pay too much money. So I want you to think a little bit about what you learned about the electricity grid during your readings. What types of extreme weather events pose particular vulnerabilities for the North Carolina grid? And you can think about the types of extreme weather that we experience here. It's been a while since we experienced a really bad drought, but there were significant droughts here in the early 2000s and then towards the end of the 2000s, in 2007 and 2008. We are vulnerable to heat waves. We are vulnerable to extreme weather, like a polar vortex that can suck Arctic air down into the middle part of the United States. We're certainly vulnerable to hurricanes, so wind speeds and flooding associated with hurricanes, and all of these can impact the electric power grid. And you may have experienced some of that, especially during extreme storms. And so we want to also think about, especially, and this is going to be kind of a focus of the game we're going to play, how decision makers in North Carolina are planning to balance this need to, number one, reduce greenhouse gas emissions from the electric power sector, while also maintaining reliability, especially with respect to resilience in the face of growing extreme weather, and costs, right? So cost is a really big one. And I think that's one that both utilities and consumers care a lot about, and we want to minimize to the extent possible. But the reality is, when we talk about a sustainable grid moving forward in the future and a resilient grid moving forward in the future, you get what you pay for, right? So a lot of the costs that or the things that we want out of our electricity systems are worth paying for. But there has to be a balance between how much we're willing to pay for that and the benefits we get from that. And those are all issues that decision makers in North Carolina have to navigate. So if there are any questions, you could check in with your TAs at this point. I'm sorry I can't be there to field any. I would like this to be more interactive, but unfortunately I can't be there in person. So I did want to introduce the sort of activity for the in-class portion of today. And so what the goal is for you to be in groups of about 5 or 6 students. And you are either individually or collectively going to kind of make believe that you are representatives from different types of organizations in North Carolina, all of whom have a slightly different perspective on the goals for what we want the electrical grid to look like, the costs associated with needed investment, the benefits associated with needed investment, and some of the risks, right? So what you might be afraid of happening if things don't go exactly the way you envision. And so there are certainly more stakeholders than what I've listed here, but these are some of the really important ones that are actively involved in the planning process in North Carolina to figure out what the grid's going to look like in the future. And so first on the list here is something called the North Carolina State Utility Commission. So the Utility Commission in North Carolina is part of the state government, and there are a group of commissioners, men and women who are appointed by the governor, whoever the governor is, and they serve multi-year terms, and they are in charge of saying yes or saying no to different types of infrastructure that's proposed by utilities like Duke Energy or North Carolina membership cooperatives. And they say yes or no kind of on behalf of electricity consumers, right? of which we all make up a part. So all of the infrastructure that we need to produce electricity, to send it to people's homes and businesses, has to be constructed and it has to be paid for. And the Utility Commission's job is to make sure that a company, a utility like Duke Energy, isn't building too much stuff that we don't need. And their job is also to make sure that Duke Energy is building the right amount of stuff so that we do have reliable electricity. And the other really key part of what the Utility Commission does is it makes sure that Duke Energy is charging prices that are fair, right? And making decisions that keep prices as low as possible for consumers. So you could think about the North Carolina Utility Commission as sort of like a regulatory watchdog. They're there all the time trying to make sure that the electric power grid is being thought of and built in a way that benefits the citizens of North Carolina, but they pay especially close attention to how much it costs for electricity consumers. So the next entity on this list is Duke Energy. So Duke Energy is a publicly traded, meaning you can buy stock in Duke Energy and sell stock in Duke Energy on the stock market. So shareholders technically own Duke Energy. They are an investor-owned electric utility. And that means that they are kind of like a private company. They're not part of the state government. And their objective is primarily to make profits, right? Now, the State Utility Commission has very strict rules about how much profit Duke can make. That's part of the Utility Commission's job. But as long as Duke Energy is following the law and providing reliable electricity to consumers in the state, the Utility Commission allows Duke Energy to set prices, to charge prices from consumers that cover their costs of doing business, meaning the costs of building and operating all the infrastructure that we need in the state, and then also covering some profits for shareholders. And Duke Energy, in terms of all the different jobs that happen at a place like Duke Energy, they have responsibilities to think about how the state is growing and what new infrastructure we might need, electric infrastructure, to make sure that they're able to meet growing demand for electricity. They're constantly monitoring the state of the power network in North Carolina and trying to identify if we need to upgrade pieces of it to make it safer or more reliable. And then a big part of their job is operating in real time on a second-to-second, hour-to-hour, day-to-day basis, all the different generators that we use to produce electricity, all the different transmission lines and substations that we use to send that electricity to consumers. And all of that has to be perfectly synchronized. So that's Duke Energy's role, is the primary energy producer in North Carolina. Another type of energy producer in North Carolina are North Carolina electric membership cooperatives. So these are publicly owned, meaning they're not necessarily profit oriented. They're owned by their own customers. And these are kind of like community electricity providers that primarily serve rural areas. And this has to do with sort of the history of the electric power sector. When the United States was first being electrified in the late 19th century, early 20th century, companies like Duke Energy didn't want to electrify all parts of the United States. It was more expensive for them to run lines out to rural areas, and they had less of an incentive to do that because they were going to end up selling less electricity to people in rural areas. So there were big parts of the United States, rural areas, that didn't have electricity service where urban areas did. And so the federal government allowed for the existence of and supported the existence of electric membership cooperatives. And so these are publicly owned community utilities that provide a big share of their own electricity, but they also buy electricity from Duke Energy to deliver to their own customers. The third entities on this list are renewable energy developers. So you might be aware of some companies like this. Examples that are located in the Triangle are Strata Solar, Cypress Creek Renewables. So these are companies that don't directly serve electricity to end use consumers, but what they do is build solar farms and they build wind farms. And then they sign contracts with companies like Duke Energy or the North Carolina Electric Membership Cooperatives to sell those utilities, the output from their solar farms or their wind farms. And then Duke Energy or the North Carolina Electric Membership Cooperatives then sell that solar and wind to us. The fourth or the fifth group on here are nonprofits or non-governmental organizations that advocate for action on climate change. So you could think about these as like policy think tanks or lobbyists that are really interested in doing something quickly about climate change by reducing greenhouse gas emissions from the electric power sector. The last group on here are industrial and commercial businesses. So factories, right? Or really large big box stores, entities that consume a lot of electricity and depend on cheap, reliable electricity as part of their business. So those are the 6 groups that I want you to think about what their perspectives are, especially in the context of thinking about how we want to design the grid in the future. So we will also want to understand what to measure when we talk about sustainability in the future or resilience, right? So sustainability meaning being able to exist over the long term in a way that balances or promotes environmental health, human health, equality, as well as economic development. And resilience, right, meaning we have a system that can withstand shocks, whether those are physical risks like an outage caused by extreme weather or some sort of financial and economic disturbance. So there's a lot of different ways to measure those qualities when we talk about the electrical grid. Some really common ones would be cost, right? So whatever it costs to build and to operate the grid in North Carolina ultimately has to be paid by the people who use that electricity, which would be you and me, and basically everybody else you know. So again, the Utility Commission's job is to make sure that that cost is reasonable and in fact as low as possible within the constraint that we also want it to be reliable, right? And sometimes there's a trade-off between cost and reliability. If you want your system to be perfectly reliable no matter what happens, sometimes that means building a lot more stuff, and that can be expensive. But if you want your system to be as cheap as possible, that means building less stuff and accepting more of the risk that sometimes you might have power outages. So balancing that is something that can be tricky, but is also mostly the job of the North Carolina Utility Commission. There's also lots of types of environmental performance that we care about. We're going to talk a lot about greenhouse gas emissions, especially in the context of this game we're going to play. But there are other types of environmental pollution that can be caused by the operation of electric power plants, especially fossil fuel-based power plants like coal and natural gas. They can produce other types of air quality pollutants like fine particulate matter, sulfur dioxide, and nitrous oxide, which all directly harm human health, especially for people that are old or have sort of pre-existing conditions like asthma. Water usage is another one. You might not realize it, but actually different types of electric power plants use and consume a lot of water. That includes nuclear power plants, coal-fired power plants, and natural gas power plants. And the primary use of water in those plants is actually as a coolant, the same way your car's engine requires coolant too. The other type of performance that we care about is reliability, meaning how many hours out of the year do people go without electricity because of some sort of failure on the grid? And sometimes that can be malfunctioning equipment, and other times that could mean some type of severe weather causes an outage. So keeping all of this in mind, we're going to play Generate, which is a game of energy choices that's been produced by the United States EPA. And this is a really simple way to think about um, how to plan an energy system to meet consumers' demand while also trying to balance trade-offs in water consumption, cost, environmental footprint, meaning emissions of carbon dioxide, but also other types of air pollutants. So everybody should have access to a PowerPoint file. In that PowerPoint file, there's going to be a couple things that you notice. One is a game board, right? And there should actually be 3 different game boards because we're going to play the game 3 different times. And each time the conditions are going to be a little bit different. But the game board looks like this. It's all these different rectangles. And each one of your teams, you should work together with your team to make decisions about how you want to fill in this grid, the gridded area. And the decisions you make are going to be related to what types of power plants you want to use to meet electricity demand. And you could think about all the open space on this grid as our collective demand for electricity. And in order to meet that demand, you have to cover all of that space with different types of power plants. Here are the different types of energy pieces that you can use, and each one represents a different type of power plant. We have fossil power plants, and those could be coal or natural gas, and there are differences among different types of power plants in the fossil fuel categories. We have existing coal plants, and those plants would represent a plant that already exists, that's already built. We don't have to borrow any more money to construct it. It's already, operational, being able to produce electricity. There's other options for building new fossil fuel power plants, both coal and natural gas. And you'll notice some important differences when you think about a new fossil fuel power plant versus an existing one. Namely, new power plants cost a lot more money because you have to borrow money to build those. In addition, there are nuclear power plants, both new and existing. Different types of solar power plants. We have small solar power plants, large ones that have batteries. Same goes for wind. We have large wind power plants, small wind power plants, wind with batteries, and then bio-based energy. So let's take a closer look at some of the different characteristics of these energy pieces. So I mentioned earlier that the purpose of the game, right, or the objective, one of them, I guess you could call it kind of a constraint, is that you have to fill in all the area in your grid. And you have to do that by placing these energy pieces on the grid. And you'll notice that in your PowerPoint presentation, when you're looking at the different game pieces, they have different shapes. And the shape or the size of the energy, so what the area is in terms of those rectangles on the grid, is how much energy that particular power plant can produce, right? So how tall it is, how wide it is, essentially gives you a sense for how much it can contribute to meeting electricity demand. There's a couple other really important pieces to think about too. In the top right corner, there's going to be a red number for each of the pieces. That's the purchase cost, meaning kind of like the sticker price for the power plant. How much it would require, how much money would you have to borrow if you were an electric utility to build that power plant? The other cost associated with some of these power plants is the annual cost, and that's the black number in the bottom right. The annual cost is kind of like how much does it cost once you've already built the power plant to operate it every single year. And in the case of a natural gas power plant, a lot of that would be how much does it cost to buy the natural gas fuel that you're going to burn to try to produce electricity. Or in the case of a coal plant, how much does it cost to buy that coal that you're going to burn to produce electricity? And you'll notice that fossil fuel power plants have annual costs in the bottom right that are greater than zero. But one of the advantages of wind and solar is that once you build the power plant, you don't actually have to pay any costs. And so they have lower annual costs. or zero annual costs. And then in the bottom left, you'll see two different ways that we're going to measure environmental impact. The carbon dioxide emissions associated with the power plant are written in green. So that number gives you a sense for how much it would contribute to global warming. And then the blue squiggly line is a measure of air quality impact. So how much does it produce air pollutants like fine particulate matter, sulfur dioxide, and nitrous oxide that directly harm human health. So when we're thinking about placing the energy pieces on the board, your objective, the thing you're trying to do the best at, is to provide electricity at the lowest possible cost. So when you're thinking about cost, at least for the first round, you want to pay attention to those numbers on the right-hand side of the pieces. And the way you calculate the cost associated with a single piece, a single energy piece, is the purchase cost, so the red number, plus the annual cost times 30. Because we're going to assume that whatever decision you make about building a power plant, right, or including a power plant on your game board, that's a decision that's going to last 30 years because that's the typical lifetime of a power plant. So for example, for this natural gas power plant, its cost, its total cost, would be 63, which is the purchase cost, plus the annual cost, which is 7, times 30, for a total cost of 273. So again, for the first round, what we're going to try to do among your team, right, you want to minimize the cost of filling in this grid. And you'll have more energy pieces than you need, right? So you're going to have to make a choice about which ones to include and which ones to exclude. And I want you to take about 20 and 30 minutes to do this. So here are some guidelines and rules for how you do this. You should be able to open and have access to a PowerPoint file called Generate Board Pieces. And so that has several different slides in it, and they're sort of organized by which round, right? So there's 3 rounds, 1, 2, 3, and I want you to start with the round 1 board and the round 1 set of pieces. So those pieces would be right after the round 1 game board and right before the round 2 game board. So the rules are you can't alter the size or shape of the pieces, right? So what you want to do is copy and paste them from where they are onto your game board. You also have to cover the entire grid with energy resources. That means you would be meeting demand, and your objective, again, is to minimize the cost, right? We're not thinking right now about carbon emissions or different types of air pollutants. You want to put yourselves in the shoes of an entity that's just trying to make things as cheap as possible for citizens in North Carolina. So there's an easy way to calculate the total cost. So if you open up the Excel file called generate_scorecard and go to the calculator worksheet, there's actually something already set up for you where all you have to do is put in the number of each type of power plant, and at the bottom, it will automatically calculate the total cost for you. So this should make it pretty quick to do some experimentation. Now, for the round 1, make sure that the cell that's located, that's called CO2 cost, is set to 0, because right now we're not thinking about the cost of CO2. And when you finished, after about 20 or 30 minutes, use the scorecard worksheet of the same Excel file to then record your solution. So I want you to write down the number of each plant that you used. And then at the bottom, record of that solution, record what the total cost was, CO2 emissions, water consumption, and your air quality impacts. So again, this is just an example of the calculator worksheet. And so again, you want to make sure that that CO2 cost is equal to 0. And then the only thing you have to do is, as you're putting pieces on your game board or taking pieces on or off or discussing among your team, you want to record the number of each type of power plant in column B. So if I were to choose one new nuclear power plant, I would put a number 1 right by the new nuclear section. And then you'll see, as you populate those values, you can go down to get the total cost in column B on line 22, I think that's 22. And then when you're done, right, after that first round, you can go to the scorecard worksheet at the bottom of this Excel file and record your answers and record your performance metrics. So cost, CO2 emissions, water consumption, and air quality health impacts. Okay, so this is a place for the TAs to stop the lecture and stop the video and allow the teams to do this for about 20 or 30 minutes. And then I'm going to talk about what to do next after everybody's done. So after 20 or 30 minutes, each team should spend a little time talking about the strategy that they used to pursue the minimum cost in round one, right? So you didn't have to think about carbon dioxide or environmental impacts at all. I wanted you to record those, but that shouldn't have been part of why you were putting pieces on or off the board. And what you should have noticed is that the general strategy for minimizing costs in round one was to make as much use as possible of existing power plants. And that's because they already exist and you don't have to borrow more money. So those purchase costs, the red numbers in the top right-hand corner, were a lot lower for existing costs. And so if you relied mostly on existing power plants, you probably got as close as possible to minimizing the costs. So one thing that I would like you to do in the next minute or two is actually go to the piece summary in the Generate Scorecard Excel file and identify the total number of squares covered by each energy technology category in your solution, right? So the nuclear power, if you go to the piece summary, it'll tell you, like, for an existing nuclear power plant, how many squares or rectangles does it cover? And the total number of squares, I think, is 342 on your grid. And so what I'd like you to do is figure out the percentage of the total grid that you have by energy type. So what fraction of your grid is covered by nuclear? What fraction of your grid is covered by coal, natural gas, solar, and wind? And then what I'd like you to do is go to the EIA's website, and the link is down here, and click on that, and it'll take you immediately to a graph that shows you roughly how much electricity generation from each source is used in North Carolina to do some comparison. And if you click on that link, it should take you to something that looks a bit like this. And this information is just for July 2021, but it does give you a pretty good sense of what types of electricity we're using in a place like North Carolina as of 2021. So you can see that the leading source of electricity generation in North Carolina today is natural gas-fired power plants, followed by nuclear. Then we rely mostly on coal, and then non-hydroelectric renewables, which is mostly solar power in North Carolina, followed last by hydroelectric dams, which actually wasn't a part of your game piece. So the last thing that we want to do for this round one is stop and think about the strategy that you use to minimize cost, right? And we talked about using existing power plants, right? And we didn't think about as much carbon dioxide or other air quality issues, right? And even in North Carolina today, right, we're using a lot of fossil fuels still, a lot of a lot of natural gas and a lot of coal. So think about how each one of these organizations that I described earlier might react to this status quo, right, generation portfolio, right? Mostly natural gas, then nuclear, then coal, then solar, and then hydropower. So think about how the State Utility Commission, whose job it is to protect consumers and make sure electricity prices are fair. How would they feel about a strategy of mostly making use of existing power plants to minimize costs? They would probably feel pretty good about that. Duke Energy, the state's major private electric utility, how would they feel about a strategy of mostly using the power plants that already exist to minimize costs for consumers? Same thing with the electric membership cooperatives. Those are two companies that, especially the membership cooperatives owned by their own customers, may be protective somewhat of the infrastructure. And if there's a set of infrastructure that already works, that they're familiar with, they may have sort of a bias towards wanting to keep it, especially if it's proven reliable in the past and keeps prices down for consumers. Now, think about renewable energy developers, private companies that make money by building solar farms, right, or building wind farms. They may be less enthusiastic about the status quo, right? Not necessarily because they care about climate change, but they're in it to make money too. And they have an interest in the state relying more on renewable energy in the future. Certainly, nonprofits that advocate for action on climate change would see the status quo as unsatisfactory, right? If we're not thinking about carbon and climate change when we're making decisions about which power plants to use in the future, that is time that's wasted, especially with an issue like climate change that is irreversible. Somewhat time dependent, right? We can't delay taking action on this problem forever. Otherwise, we won't be able to solve it. The last category here of users would be large consumers of electricity. Now, if you are a business that uses electricity, a lot of it depends on having that price be low to keep your own costs of doing business low, you would probably be happy with the status quo. And you might be a little hesitant about making changes that might interrupt the reliability of the power grid or make it more expensive. Okay, so this is the least cost solution, right? So compare, what I want each team to do is compare the solution that they came up with this one. And you can pause the video here at this point and allow students to compare their solution with this one. And it's totally fine if you didn't get this exactly, but you might take a moment and on your game board, you could use this as the starting point for round 2. Okay, now it's time for round 2. And the main difference in round 2 is that we are going to start thinking about climate change, and we are going to tax carbon, meaning the power plants that emit carbon dioxide, meaning they have numbers that are greater than 0 in the lower left-hand corner, those green numbers. Those are going to become more expensive, right? And the rationale here would be that producers of coal and producers of natural gas, the minute they take those fossil fuels out of the ground, would be taxed by the federal government. And that money could be used to either send back to consumers to make all of this a little bit more palatable, or they could use that money to invest in renewable energy or help move people from coastlines in the future to adapt to climate change. But what the result would be for a natural gas power plant owned by a company like Duke Energy or a coal-fired power plant would be that the natural gas they buy as fuel for their power plant or the coal they buy would now be more expensive. And that means that it would be more expensive to operate the power plant. So in this case, when we think about incorporating the cost of carbon or CO2 emissions into our decisions, we now want to include a carbon price, which means that when you go into your Excel file in the calculator, you want to make sure that the CO2 cost is equal to 1 now. And that's going to come into play when you actually calculate the cost of, per piece in each round. You're going to include the purchase cost, so the red number in the top right, plus the annual cost, so the annual cost times 30 for 30-year power plants, plus the green number in the bottom left-hand corner times the carbon price, which in this case for round 2 is going to be equal to 1. And then that also has to be multiplied times 30 because you're going to be emitting carbon dioxide every single year. And you'll notice for the round two, when you go down to the round two game board, behind the round two game board, you'll see more availability of wind and solar. So you'll have more wind farms and solar farms to choose from. So take about 20, 30 minutes and see if, again, the objective here is to minimize the cost, right? So you want to make sure that the grid is as cheap as possible. The difference in round two is we're going to be penalizing in dollars, right, any kind of emissions that are being produced from fossil fuels. So again, so the guidelines and rules for round two, you're going to go to the round two board and set of pieces. Again, you'll notice that you have an increased supply of variable renewable energy, wind and solar, from which to choose. You can't alter the shape or size of the pieces. You have to cover the whole grid. Now, what you're going to want to do in the calculator worksheet is set the carbon tax equal to 1 in cell H21. And then you don't have to worry about it. You can make your choices, right? You go to the calculator worksheet and zero it out and put your choices in about how many nuclear power plants, how many natural gas power plants. And as long as you have the carbon tax set equal to 1 in cell H21, that'll automatically include the carbon tax, the cost of carbon, in the choices that you make. So again, when you finish filling out the grid, I want you to use the scorecard worksheet of the same Excel file and record your solution. Don't write over your solution from round one. Record it next to it. Make your choices about how many of each type of power plant you're going to include. And then at the bottom, record the total cost, carbon emissions, water consumption, and air quality impacts. So here, just showing the Excel file that you want to change. Again, you want to make sure that carbon cost, CO2 cost, is set equal to 1 for round two. Okay, and after you've done this, take about 20 minutes or so. We want to talk about the stakeholder perceptions. And so this is a good place for the TAs to, again, pause the video, wait till everybody's done. So once everybody's done, let's think again about how these different stakeholders would view this latest round, right? We're now taxing carbon, probably at the federal level, right? We're going to say the federal government has imposed a carbon tax. And that has done a couple things, right? It's made it more expensive to use both new and existing fossil fuels, right? So that means that if you continue to use fossil fuels, immediately it becomes more expensive. And that's something that the State Utility Commission might feel a little bit more uncomfortable with. Now, their job is to make sure that the utility in the state, Duke Energy, the North Carolina Electric Membership Cooperatives, are following the law. And if there's a federal law that's taxing carbon, the North Carolina Utility Commission would understand that, well, the cost of using fossil fuels is going to go up. So if the choice is made to continue relying on fossil fuels, and it may not be, then that is being done, or that needs to at least be legal, right? And so, but as long as the generation mixes that you're populating on your grid are following the law, their goal is to minimize the cost, right? And so minimizing the cost in this case might mean relying less on fossil fuels, both coal and natural gas. Duke Energy, the state's major private electric utility, owns all of these existing power plants, right? And think about, right, in your solutions, what was the strategy you took, to minimize cost? In some cases, did you exclude some existing coal-fired power plants or some existing natural gas power plants? Think about how Duke Energy might view a solution, a plan that required them to abandon certain power plants that were already existing, right? Same thing with the North Carolina Electric Membership Cooperatives. What about renewable energy developers? My guess is what you found in some of your solutions is that once you start including a cost of carbon, um, your solutions become a bit more reliant on wind and solar, and that would be to the benefit of companies like Strata Solar or Cypress Creek Renewables, companies that for their business they build and sell electricity from these wind and solar farms to companies like Duke Energy. Nonprofits that advocate for action on climate change. How would they view this, right? It's not a really aggressive approach to dealing with climate change, but it's a start, right? At least we're counting or penalizing carbon a little bit. And then industrial and commercial businesses whose facilities are major consumers of electricity. Remember, they want reliability, they want low costs. What happened to costs when you when you start charging for carbon? What the cheapest solution, right? The cheapest solution is it more expensive than the status quo, right? What would that do for industrial and commercial businesses, right? As we decarbonize the grid, does that mean it's going to become more expensive? And how would these types of entities position themselves in support of or against plans to decarbonize the grid that might make electricity consumption more expensive? So your solutions for round two should be this, right? You should be using 2 existing nuclear power plants, 2 existing coal-fired power plants, 3 existing natural gas power plants, and then a lot more wind and solar, right? 4 small wind farms, 4 small solar farms, and 5 large solar farms. So now it's time for round 3. This is the final round, and it may not take you as long as 20 or 30 minutes to do this. The only difference here is that we're going to increase the cost of carbon, right? It's no longer going to be equal to 1, it's going to be equal to 4. So you need to go to your Excel file, the calculator, and be sure that you're changing the value of cell H21 from 1, which was round 2, to equal to 4. So we're dramatically increasing the penalties associated with using fossil fuels. Those fossil fuels are now going to be really expensive because when Duke Energy or whoever owns the power plants is buying that coal and buying that natural gas, there's a tax on that coal and that natural gas that makes it a lot more expensive. So same thing, you can't alter the shape of the pieces. You can only use the pieces that are available for round 3. When you finish, use the scorecard to record your solution and also record the total cost, CO2 emissions, water consumption, and air quality impacts. Okay, this is another place for the TAs to stop the video. When the students have finished with the exercise, what we would like them to do is think about the generation mix that they came up with. The same thing as for round 2 and round 1. I want you to identify what percentage of electricity demand is met by each technology in North Carolina based on round 2 and round 3. What percentage of your grid in round 3 is nuclear? What percentage of it is solar? What percentage of it is wind, etc.? And compare that to potential future generation mixes that you see listed in something like the Clean Energy Plan that's being talked about in North Carolina, or the Duke Energy Integrated Resource Plan. These are really big documents, so it helps to have gone through them a little bit before, and just try to get an idea of how your generation mix in round 3 compares to some of the ideas that are being put forward about how the North Carolina grid may evolve in the future. So here's the round 3 solution. The big difference here is that because we are taxing carbon dioxide so much, the North Carolina grid doesn't rely on coal or natural gas at all, not even existing power plants. It does keep existing nuclear, but for the rest of it, it's relying entirely on a combination of wind and solar. So by now, you should have been able to record and then also compare across all 3 rounds the performance of your grid. And I want you to compare it in terms of cost, environmental performance, so CO2 emissions, air quality pollutants, and water usage. And what I want you to pay attention to is whether you see some trade-offs, right? Across the three rounds, what happens to cost? What happens to greenhouse gas emissions? What happens to air quality pollutants and water usage? Do some of those solutions look like they're better or worse in some categories than others? Is there a trade-off, right? Are we going to reduce the environmental damages associated with the grid as a function of cost? Meaning we have to talk about them side by side as part of the same thing. Well, you get what you pay for, right? You get, if what you choose to pay for is lower emissions, then think about, would you be willing to pay for that? Would your parents be willing to pay for that? Would your neighbors be willing to pay for that? Would people that you disagree with politically be willing to pay for that? And that's the reality of the situation that we're in. Everybody feels a little bit differently about what they prioritize here. And we have to come up with solutions that meet all of these different objectives. And the reality is we can't. There's no silver bullet. There's no way to create a grid of the future that's the cheapest possible thing that doesn't have any bad pollution associated with it, right? That's what makes this issue so hard, right? Is because there is this sort of trade-off, and not everybody agrees on what that optimal solution is. So circling back finally to an issue that didn't come up at all when we were thinking about the generate game, right? We didn't talk about weather risk and reliability much at all. And that's a little bit strange because we know that in the future, right, climate change is going to create more frequent and severe extreme weather. And also, as we decarbonize the grid, you should have noticed that we rely a lot more on wind and solar. And wind and solar is not always reliable, right? And so what I want you to take a couple minutes to think about, and this should be a part of a TA mediated discussion, I would say, is how do you think we would think differently about placing different pieces on the board? And the answer may be we don't at all, if we're also trying to make a decision about reliability, right? Does it alter what type of generation we would put on the board, or the amount of generation capacity that we need to build? And why don't we discuss that for a couple minutes, and then I'll offer my thoughts. So pause the video. Okay. So, one of the things, and I kind of alluded to this earlier in the lecture, is this, what we saw in the last slide, or you should have, is that there is this cost, but the trade-off between cost and environmental performance. And often what we see as well is that there's a trade-off between cost and reliability. Sometimes there's a sort of a cute phrase that people use to talk about the secret to reliability is redundancy, right? That word redundancy means building stuff that you don't need. But I would rephrase that a little bit and say redundancy in terms of the electrical grid is building stuff that you don't need until suddenly you need it very badly, right? When we think about heat waves affecting much of the western United States this summer, and severe winter weather affecting Texas in February of 2021, both of which caused massive costs to increase and also caused people to lose power during periods of the year when extreme temperatures outside make it really dangerous to not have electricity. Both of those are kind of lessons in the need for redundancy, right? And one of the big issues to come out of the Texas disaster in February of 2021 was the failure of certain types of power plants, right? When the grid needed electric power plants the most, they didn't work. And part of that was having wind farms that we would like them to be working and they wouldn't work. A larger part was the failure of certain types of natural gas plants whose components froze because the weather was so bad. And so when you think about averting those types of disasters in the future, most of the solutions that we think about, right, as planners, um, is to build more stuff, right? And that means that the even if demand for electricity on average stays about the same, we might have to think in the future about adding more redundancy, right? Building plants that we might not need all the time, but we might want to have around in an emergency. That's also a way to think about grids that are entirely reliant on wind and solar. In that third, at the end of round three, you should have found that the grid was going to rely on nuclear and wind and solar. The issue with that is that nuclear power plants aren't really very flexible. You turn them on and you basically leave them on all the time. You can't ramp them up and down. And one of the truths associated with relying more on wind and solar in the future is that you need something to be available when wind and solar are not, right? On cloudy days, right? Or on days where there's no wind. And usually that means some type of power plant that can turn on and off really quickly. And so that round three solution that we actually came up with is almost impossible, right? You can't have just nuclear power plants and then wind and solar. You would probably need to have large scale battery storage, and you might actually need some natural gas power plants almost as backup. The plan wouldn't be to use them all the time, but you might need them around in case you go through 4 cloudy days in a row, right? Or 4 days with no wind in a row. Otherwise, you might lose power service, right? And people might experience outages. Okay, we've come to the end, and the end of the case assignment is written here. It looks like it's kind of cut off. So maybe please just use the Word document that I shared that the TAs should have access to for the full prompt. But we're going to try to put everything together in a 5-paragraph essay. And what I'd like you to do is describe your ideal strategy, right? Based on this exercise and everything you picked up from the readings, describe a strategy for North Carolina to decarbonize the state grid by 2050. This is very relevant because the North Carolina Senate just passed legislation targeting a fully decarbonized grid in North Carolina by 2050. And at the moment, they don't know how they're going to do it, right? They're going to try to study the issue for a couple years and come up with a plan. But this is a question that we don't have an answer to. And so I want you all to help answer it. All right, that's it from me. Thank you very much for participating. I'm sorry I couldn't be there in person. I hope to meet some of you a little bit later on, especially if you take ES 300, which I teach in the spring and fall and summer. All right, talk to you soon.